Okay, so it's a minute past 3. We've got the attendees is racking up, so it'd be great to make a start. So everyone, welcome everyone to the March AgriFoRwARDS CDT seminar series. It's a beautiful sunny day here in Lincoln, and I hope that you will all have some time later to enjoy the sunshine as well. Just to introduce myself, my name's Garry Clawson, and I'm a cohort 3 AgriFoRwARDS CDT student, currently reading for my MSc in Robotics and Autonomous Systems. And it's my pleasure to be your host today for this event. Alongside me on our student panel is Rachel Trimble, also part of the AgriFoRwARDS CDT cohort 3, also reading for the MSc in RAS, again here at Lincoln. And I would also like to introduce Rupika Rabikana, a CDT cohort 1 student, currently halfway through their PhD research, again here in Lincoln. So welcome panelists, welcome viewers. It's a pleasure to be here with you today. So with that, it's my deep pleasure to introduce our fantastic speaker today, Dr Ayse Kucukyilmaz. So Dr Kucukyilmaz will take us on a wonderful journey through dynamic role allocation and shared control in human-robot collaborative teamwork. I feel this is such a timely discussion as we emerge from COVID, but more so with pressing inflationary costs impacting industry across many sectors, but really hitting hard the food sector, all the way from farm to fork. Human-robot collaborative teamwork will be a game changer here. Dr Kucukyilmaz's CV is long and varied. Their research focuses on haptic shared control for physical human-robot interaction with the aim to build adjustable autonomy paradigms that enable dynamic switching behaviors between different levels of robotic autonomy during shared control of physical tasks. A broader stroke of research interests also include haptics, physical HRI, assistive robotics, and as well as machine learning. Ayse is currently serving as Assistant Professor of Computer Science at the University of Nottingham. Previously, Ayse was a senior lecturer and member of the Lincoln Centre for Autonomous Systems, so is well known to the school, certainly here in Lincoln. Between 2015 and 17, Ayse worked as Assistant Professor at the Department of Computer Engineering at Yeditepe University, having previously to that, having held a postdoctoral research associate at the Personal Robotics Laboratory at Imperial College in London. Ayse received her PhD in Computational Sciences and Engineering in 2013 from Koç University in Turkey, and obtained her BSc and MSc degrees in Computer Engineering from Bilkent University in Turkey. Ayse is the recipient of numerous awards and received individual fellowships from the Marie Curie Actions and Tubatech. Complementing that, Ayse also holds grants from EPRC and CHIST ERA. So I'm sure you'll agree with me today that today's session is going to be extremely engaging, and I ask you to keep posting your questions into the chat throughout the presentation, and once the talk is finished, we'll absolutely open the floor to the audience panelists to get those questions through. So without further ado, I'm really pleased to welcome Ayse and to give us this wonderful talk. So please, over to you, Ayse. Welcome.
Thank you. This was such a nice introduction. I'll just share my screen. Hopefully this would work. And if I Okay.
Okay, absolutely perfect. Ready to go, cooking on gas. Please, over to you, Ayse.
Yes, thank you. I'm still having a minor issue, sorry, because I can't now see my slides. It's very embarrassing. We should have tested this, right?
It's no trouble. There's always one hitch, so don't worry. Oh. This is ours.
Yeah, I didn't expect this. Just a second. No, I completely missed all my screens. Okay, I'm on. Okay, do you see everything?
Okay, brilliant.
Brilliant. Yeah, we started like in 5 minutes. I set up my screen. So thanks for inviting me. It's really nice to be around you. I was looking. I only know a few of the names. I think I interviewed Rupika and I know Gary, but apart from them, you're all new. So congratulations on your journey. And let me tell you a little bit of what I do. So I'm a assistant professor in the University of Nottingham, and basically this slide talks a little bit about my journey in research. I started my PhD in 2007 when I was doing more really like haptic interactions in the virtual worlds, where I was playing with this haptic devices, as you can see here, which is a phantom device which can directly transmit you force feedback from a virtual world. In 2010, I moved on to the Technical University of Munich because during my PhD, I was basically developing games, and we were looking into role distributions, role exchanges within the games, and that had direct implications for human-robot interaction. So all these game ideas came into, okay, what happens if we have a robot which actually carries something with a human, and what if that robot can exchange roles like leadership, followership kind of roles with the human. And I played with this robot called Eddie, and we were playing with a table to carry it within a space, and we were looking at whether the robot can understand my intentions through the forces to lead me better while carrying that heavy, bulky load. In 2013, after finishing my PhD, I moved to Imperial College London, where I worked on an intelligent wheelchair. And the wheelchair is a device that you sit in. So it's a perfect shared control device, which can guide you. And I was trying to implement guidance mechanisms to share the control of the wheelchair with a person that drives the wheelchair. In 2017, after a kind of a teaching post in Turkey, I moved to University of Lincoln. I joined ALCAS, and in ALCAS, I mainly worked with the Franca teleoperation setup. However, we did also collaborate a little with Mark, which we're hoping to continue at this stage with some opportunities coming up. And I did some work also within the museum environment to make a social robot to be taught to recover from errors, to learn from human interactions as well. In 2020, just before COVID strike, I moved to Nottingham, which wasn't the best time to make a move, I would admit. And in Nottingham, I'm doing quite different things. I'm still working on the teleoperation setup, but I do a lot of work on social robots. Now I have a research thread which is going on telepresence robots, which are iPads on wheels, and how those kind of devices can actually connect people in a better way. How can they have more socially capable navigation capabilities, etc. And I do work with human-human interaction as well. So just before starting, and today I have a little bit more material, I think, than usual, so hopefully it will fit in the time. I want to talk a little bit about robotics at Nottingham. So in the computer science department, robotics is quite new. We are based in this Cobot Makerspace, which is a laboratory that covers kind of 100 square meter area in a separate building, which has certain open area which is reconfigurable for social robots, robotic arms, manipulators, and experiments. We also have a living lab, like an area which we are converting into a space with a sensor network. We are interested in looking at more socially or assistive robotics and understanding how people actually behave within those environments. And all the Cobot Makerspace is actually managed by our ops team that is in the right corner. So I'd like to also say that they are actually managing the whole operation of the space. And I'm a member of two research groups at the moment. So the first group is Mixed Reality Laboratory. Basically, the laboratory is a virtual augmented reality laboratory, but they are actually interested in looking into more interdisciplinary approaches to enable any kind of digital technology, which includes personalized interactions with embodied devices, which are robots. And this year we have found a new research group, which is CHAT, Cyber Physical Healthcare and Assistive Robotics Technologies. We are currently 4 academics. The group is led by Preminda Caleb-Soli, and we are looking into more socially and physically assistive robots, more smart sensor technologies, and accessible interfaces for people. And the research that I do covers these, but also extends to different industries as well. And one of the things that we were working on in the last 2 years was a little bit towards autonomous robotics, because we really couldn't do much human research in the last 2 years. And I am currently leading this project called HEAP, which is a CHIST area project focusing on human-guided learning and benchmarking of robotic heap sorting. And the challenge of the HEAP project may be familiar to some of you, because it's very similar to the NCNR project. It's a spin-off of the NCNR project, actually, that focuses on nuclear decommissioning and those kind of scenarios where you have these clutters of objects which the robot needs to manipulate. And our aim is to develop benchmarking algorithms for manipulating interesting objects. So what we are doing is we are trying to come up with realistic simulations, reproducible setups, which are real setups, so that simulation results can be transferred directly to the real robot, and some object models. And benchmarking is quite difficult, and especially a big problem in robotics, because unlike many sister resource fields like computer graphics, we don't actually do too much benchmarking as of yet. Because we all work on different setups, we all work on different tasks, and any algorithm that we develop always has the problem of, is it really good? Is it really the thing that actually advances? And this HEAP project is an effort to at least have a place or have an environment which people can actually come and implement their algorithms and maybe have a better chance of benchmarking the results in a more objective manner. And the efforts that we have done over the 2 years in the HEAP project has been to create certain data sets and a simulation framework. So I won't be running these videos, but the object data sets we have are focused on different aspects. So there is one grasping data set which consists of procedurally generated objects. They are 3D printable. You can access the CAD models from our GitHub repository. There is also a grasping data set which is produced by INRIA, which has different rigid and soft objects which are collected incrementally into heaps. And there's the object clutter indoor data set, which is created by the Technical University of Vienna, which is incrementally again built to form cluttered scenes. And the simulation framework we do use has been also used in Lincoln for quite a while. I think it is still being used. So the framework is based on the simulation lab software. It enables real-time control of control and communication. We have now integrated PyVolut and Mujoko physics engines into it. And we are now working into debugging certain aspects, which makes the simulation and real robot interfaces the same, so that we can transfer the same code between the simulation framework to the robot. There's also OpenAI gem integration for the simulation framework as well. And this is now kind of an older version, is disseminated through the ALR GitHub. So some of the work we did for benchmarking within the HEAP is the development of a grasping pipeline. So most of the work in this slide is done by IIT, by Lorenzo Natale's group. And one of the bigger outputs of the project has been the GRASPA grasping performance benchmark. So this pipeline basically gives you a set of objects, different difficulty layouts that you can use, and the definition of grasp poses with respect to the printable boards, so that you can actually come up with the same scene, put your grasping algorithm, and say that I actually scored this much in your tests. So we do have a standard protocol to evaluate the grasp success. We have certain grasp quality measures. We have reachability and calibration measures as well. So you have a chance to understand whether your algorithm is failing from calibration kind of issues or maybe reachability kind of issues as well. And currently in Nottingham, what we are doing is we are using the simulation framework and we are trying to move some of the grasping algorithms that we implemented to the real robot in parallel, so that we can give an understanding of something that works in simulation how well something that works in simulation reflects back in the real robot. And with the simulation, we do actually have problems. For example, in the scene, you can see that the robot actually grasps a hammer, which is really not very, very realistic. You could never grasp a hammer like that, but this is a successful grasping exercise in the Mujoko simulation environment. And our benchmark results, because they are not published yet, I can't really show here, but they do illustrate that there are very much differences in even different simulation software. And then when it comes to the real robot, we are trying to understand why these are happening and give some kind of better perspectives into what is the situation, so that whenever you get some result, maybe you can just contemplate on it better. Another thread of work at Nottingham was on the benchmarking of the clutter. So Barish, which is one of our postdocs, has been working on this scenario for a while, and the aim here is to push objects to see the scene better. In here, what you see is a mask of the scene, and the red objects are the objects that are kind of on top of each other, so they are not nicely segmented, and the robot is trying to push around all the objects to see them better. And for this benchmarking scenario, we implemented really very few algorithms, because the benchmarking for this kind of an application is quite a new idea. There is only the visual pushing and grasping paper, which is an IROS 2018 paper exists, and we implemented that, and we came up with some heuristic baselines, which are like random actions of pushing the scene, and we compared our approach with these. And our approach is basically a two-layer model. On the top layer, there is a mask RCNN trained with depth data to generate rewards. And on the second layer, we have a DQN layer, which is trained with the RGB data and is used to select the directions to push the objects, given 16 discrete directions to push objects. And this work has been just accepted in ICRA, and if you're around, it will be presented in May. So these are the things that we do in terms of autonomous robotics, but this talk is mostly about human interactions. And some of the results that we have for benchmarking, simulations, etc., they do also demonstrate that autonomy is a very difficult thing to achieve, especially when it comes to more complicated environments, such as a clutter, which is not a very difficult environment for a human. But for robots, as you already know, because you're in one of these very difficult fields, which is agri-robotics, achieving autonomy is very, very difficult. Robots really fail, they fail miserably, and whenever they fail, they need human help. And this is one of the figures that I started using. When I was doing my PhD, I was trying to draw these figures myself, because there was no concept about this spectrum of autonomies. Now it's everywhere. And there is this spectrum, basically. This is 5 levels in the autonomous driving, but I see this as a spectrum of behaviors where there is no automation and full automation, which is something like a Wizard of Oz or teleoperation, and fully autonomous operation. And in between, there are all these kinds of different behaviors that you can implement. And I tend to call them human in the loop, because they are in some ways putting a human either sequentially or simultaneously in the loop with a robotic autonomy. And the human does something, whereas the robot also does something. The area that I work on is called shared control. And shared control has, I think, a few nuance differences than human in the loop. So shared control is a subset of human in the loop, because we can also have these applications where you trade the control to the robot, you supervise the robot, and so on. And shared control is, although sometimes used to cover all of these things, is, in my point of view, different. So the way that we implement human in the loop for the heap scenarios is through teleoperation. So what we do in heap is we have this teleoperation setup, which consists of 2 Franca arms, and we use this setup to provide guidance to the people whenever the task gets very very difficult. And our framework is based on this architecture, which my student Jayant has came up with when he was doing his master's in Lincoln. And it's a force feedback architecture for the Franca robots, which is able to provide contact forces from the environment and virtual forces that you can develop within any scene. So it could be repulsive forces, it could be attractive forces, etc. And we are, so this architecture is for any kind of morphologies, but if you have a Franca robot with torque sensors in each joint, you can basically send the torques to the other robot arm and feel the environmental forces, and then you have to come up with a mechanism to merge this with virtual forces because they could collide with each other. So one work we did, which was kind of interesting afterwards, was a guidance mechanism based on human intentions. And in this work, we used the same architecture and we combined it with some inference about human intentions. And in this task, what we are doing is we have these small objects around, they are colored, and the robot knows how to grasp each of the objects, but the robot doesn't know what to do with the objects. So the task here is to put the red objects into the red bin and the yellow objects into the yellow bin, and only the human knows this task description. Basically what happens here is based on the approaching directions of the human and how well that motions fits pre-learned PRAMP trajectories, we are applying adaptive guidance to the robot to select one of the objects and reach them. So here, basically, the researcher is playing around to see that, say that like I'm now moving towards this bin, so it's probably that one. I'm now moving toward the yellow, so the decisions are changing. So the intentions are changing and the guidance is adaptively actually changing to move the robot arm to go easily towards one of the bins or one of the objects, depending on the sequence of the task. And the sequence of the task is decided on the fly, looking at whether I have an object in my arm or whether I don't have an object in my arm, and whether if the objects are moved, it can dynamically change the PRAMP trajectories to reach to the correct object location, unless you don't really throw away the object too far. And this was one thing that we did for implementing haptic guidance. And afterwards, we did an experiment, and all my work comes with an experiment, actually. We tried this system with human participants, 12 people. We compared between the manual mode, where people actually did the task on their own, versus a guided mode for 3 trials of 4 objects in the same per condition. And we couldn't actually find out any advancements in the number of correctly sorted objects, but we saw that in terms of the task smoothness, the trajectory lengths, guided mode actually improved the operation significantly. So the spectral arc length measure is a negative measure. So whenever you're in the positive direction, your smoothness is actually better. And we are looking into this kind of different metrics when we are working with humans to understand what kinds of elements those kind of guidance is actually helping. Because also with the discussion of the benchmarking, your metrics do matter, especially when it comes to humans. Sometimes the task performance doesn't really matter. Sometimes it's about how comfortably you did the task. And these are the things that we are trying to find out when we are doing all our experiments. So I did talk a lot about haptic guidance and so on. So in these experiments, what we were looking at was there is guidance. So it's a very standard way of implementing haptic guidance on robotic arms. You implement a trajectory, which is typically called a virtual fixture in haptics, and you move the robotic arm to that virtual fixture, and it guides you all the time. However, if you read a little bit more about the haptics literature, a better way of implementing shared control has been actually suggested 20 years ago by looking at this horse metaphor. So what these studies actually say is that the perfect shared control system is a horse. Because the horse has autonomy, the human has autonomy, but also when you're riding a horse, you're actually controlling the system. So it's not like deciding on its own all the way, but you have reins. So as the user, you actually control how the autonomy changes. So much of my work actually was kind of created around this idea. And I did develop role exchange schemes with humans and robots, human-robot teams. And that is one thing that we are trying to identify at the moment on what kind of behaviors you can actually assign to a robot when you're in collaboration with them. And some of my earlier work in the Technical University of Munich was on carrying heavy objects together. So this application area is, I think, getting more popularity right now, but this is one of the first studies that actually focused on this problem. And in here, what we do is we implement a trajectory for the robot, so the robot kind of knows how to do the task, but it can't do the task on its own because of the rotation. So it's a perfectly two-people task, and the robot is actually just helping me. And what we have also here is a force sensor on my gripper, so that the robot can actually sense the forces that I can apply on the table. And based on these forces, the robot can choose what is its effort sharing level, which we also call the autonomy level. And in here, we did some geometric analysis of the task, and we looked at the redundant spaces. So the redundant directions in this task is the force directions that are on the null space of the task. And in this experiment, we only play with the null space, meaning that we are only trying to make the robots exert more effort on the task without actually changing the course of the task. And the idea we had was quite simple, and it was a rule-based system where we can measure the forces of the human. We have a desired force to move the table from one point to the other. We have a role allocation parameter, which we assume at the beginning of the task. Let's say it's the human controlling the task all the way. And then a changing of this parameter. So here, lambda equals 0 means it's the robot's control, lambda equals 1 is the human's control. So what we do is very, very basic. We compute the force contribution of each agent based on the assumption of the role allocation parameter. And if the real force, the measured force, agrees with what we compute, and by we, I mean the robot, we basically say you're doing something correct, increase your autonomy. If it's not agreeing with whatever the robot is computing, we say you're probably doing something wrong, so decrease your autonomy, make it easier for the human. And that is the very rule-based mechanism we implemented for the HumanEnd Robot. And we did a study. We could see that we actually could reduce the completion times. We could actually reduce the applied forces on the task, but only if we implement it correctly. And what do I mean implement it correctly is we had actually two paradigms here on how we implement these role exchanges. So we had something like a bang-bang controller, which increased or decreased the autonomy quite harshly. And we had another paradigm which kind of looked into, which smoothed the autonomy change throughout the time based on how active the human is, how much force the human is generally putting into it, how fast he is, and so on. And the benefits of the paradigm was only visible if we did it smoothly, which means that if we implemented it correctly. And we had a lot of subjective results here as well, which also kind of showed the same results. People really didn't like the discrete scene. Actually, in this example, people really didn't like any kind of robotic proactive autonomy. They really wanted a robot that was very consistent because it was quite shaky, I guess. But this kind of an experiment gave us a lot of ideas on the implementation of these human-robot interactions. And basically, I will skip this slide, but the whole idea is based on this simple experiment I did at the beginning of my PhD, where I implemented a game which you play along with the robots. and you're basically manipulating the ball through two actors, and the robot is sometimes helping you, sometimes not helping you. And we implemented a negotiation framework in between to enable the control of the human and the robot. So they are like connected to a negotiated point by two springs, and you change the spring constants to make the robot more proactive or the human more proactive, and this is the whole paradigm. And this experiment was, I think, to me, very fundamental, because by looking at the data, by looking at what humans were doing, I could actually see that there are specific roles, and those specific roles are actually location specific. So they were actually enacting the robotic autonomy at certain points more than the others. And they were actually assigning, people were actually using this autonomy as if they are riding a horse. And of course, I moved a little bit farther away from the role definitions, and I started thinking about maybe making these paradigms a little bit more clever. So I worked on an intelligent wheelchair for 2 years, and in this example, what you see is an autonomous wheelchair, which is the worst idea that you can come up with, because nobody will like it. And there is, on the other spectrum of wheelchair users, there is this kid, for example, who has some brain injury, so he would crash all the time. So for that person, you need to ensure safety. So whereas this first person who would want control would really not like an autonomous controller, this kid could like it. And since we can't really consider all the people, because every people, especially in the assistive domain, is very, very specific, shared control solutions formulate a very nice solution for this, because you can just basically select how much autonomy you're assigning in each of these configurations. And our idea here was to put a haptic joystick on the wheelchair and make it drivable by a remote person or a person within the wheelchair. And in here, the remote person is driving the wheelchair, but I can also take control of the wheelchair and stop it as well. And this also uses the same haptic negotiation framework underlying as a paradigm to change the autonomy levels. So the main idea of the work was actually to learn the assistance paradigm for the robotic wheelchair. And we did some experiments to take human demonstrations with real people. So the remote person gave assistance to the driver in a small scene where there are a lot of rotations, and the guidance behavior was person specific based on how dangerous the person was thinking the driving behavior was. So for people, he wasn't maybe giving, actually I was giving the assistance all the time, so it's always my data. I was giving sometimes no assistance at all because they were driving quite well. For some people, I was making them very far away from the obstacles and so on. And behind this, there is a Gaussian process regression model, which learns my assistance behaviors, which are the joystick commands that I apply to the wheelchair when the other person is driving. And what I learn is the assistance commands in response to the user commands who's driving the wheelchair, as well as the environmental context and the robot's velocities. So whenever the robot is actually increasing speed toward an obstacle, and if you see an assistance command, that is kind of the behavior you learn. And in the prediction stage, we take away the assistant and we put the autonomous controller on the robot, and the robot starts helping you. In the small figure here, you see that this red line is the assistance and the green line is my commands in this example. And what the robot is trying to do is to rotate, help with the rotation. We also tried this with an example when instead of rotating, I don't rotate and I go forwards, and let's see what the model would do. And it did perform well in here, not trying to push me towards rotation, because it was actually learning only from relative data, not absolute data, so it wasn't really remembering the scene. So for this, we looked at real human data, so a human giving assistance and how the regression model can model that behavior. We saw that it was good. We did also look at some error metrics for the root mean square of the error to see how well it is. And then we did an experiment as well. So I will skip the details of the experiments, but what we saw was a comparison with the human operation. So if I have a robotic helper versus a human helper, how does the behavior change? And in here, we again didn't see anything in terms of lab completion times, for example. Obviously, the human was faster, but there wasn't too much going on. If we gave, for example, haptic sensations, or if we didn't give haptic sensations, there wasn't too much difference. But in terms of the effort behaviors, the human's operations and the robot operations were drastically different. And this is, I think, because of some kind of co-contraction behaviors when humans are adapting their motor behaviors to each other when they are driving, whereas the robot is not able to. However, we didn't really investigate on the sources of the problem, but we do see clear differences between how two humans operate and a human and the robot operates. So I do have also, based on these information, some data collected on human-human interaction when they are carrying objects together. We came up with this classification of interaction types. So the basic idea here is if you're carrying something with another human, you're either agreeing with them, or you're disagreeing with them, or you're at a neutral condition. And specifically to the task, you can maybe agree on the intention of the motion, the direction of the motion, etc., and that can come up with certain task-specific interaction patterns in the end. So we have this human-human data sets, which is labeled, annotated per interaction types as well as interaction patterns, and I have been working on this data set for a few publications, and we have been collecting also more data on smaller object-carrying experiments in the last year as well. And what we could show was in the last studies that we could actually distinguish whether people agree or disagree on rotating or translating an object only by looking at their forces. So you don't even need to see some of the information when you're completing an object transfer task, which was a very good result, because up until 2020, we were unable to get that information from without the visual information. So this kind of gives us a lot of opportunity in robotic manipulation, for example. If you're doing some collaborative task, maybe you can rely on force sensing that is on the robots, and that could actually open quite many avenues on choosing your sensors, etc. So that is much of the work. I'm also working with the Task Hub in the last 2 years. We are looking into some more interdisciplinary work. We are looking into trust in terms of human-robot teams. So we have 2 case studies at the moment. One is on disinfection of the robot, and we do more like questionnaires, user studies, in-depth interviews with people to understand what is the attitudes toward robots. And finally, we have one surgical use case, which is for the last year awaiting ethical approvals, where we are planning on actually developing some interventions to play with the robot behaviors and see how people's attitudes to robots change if the robot, for example, fails, and so on. So that is, I think, all. So as a summary, I've been talking about all these things where we can collaborate with robots, and I've been looking at things where you learn from humans to implement better robotic behaviors, and I'm hoping in the future that we can come up with robots that complement humans. And that's my journey, that's my story, and thanks for listening. It's a little bit longer than I promised, I think, but thanks anyway.
Excellent, brilliant, beautiful talk. Thank you very much. A virtual round of applause, even though we're on sort of speaker, but we'll give that. So what I'd like to say is, woo, yeah. So open questions to the audience. So please put your questions in the chat, and then we'll prioritize them and we'll pass them to Ayse. I'll start off with the first question, then we'll throw it to the panels and we'll have a discussion. Please feel free to jump in and ask any questions as you wish. So I've got something to start. So this is the first time I've seen sort of collaboration in this way. My initial perception of collaboration was robots and humans doing independent tasks together rather than a shared task, such as carrying a table or something like that. What I didn't quite get in my mind was how the tasks are broken down, or how you can decide on a task that would be suitable for sharing. Is there some sort of process that you would go through or think about when you've got that in your mind? Can you give us some sense or idea around that?
I'm not too sure I understand the question very clearly. Is it about like what kind of tasks are physically collaborative, or?
Yeah, so I noticed you did one of the later experiments was two people picking up a small object and whatnot. So it was really around what sort of tasks can you realistically do with a robot and a human. What's the boundaries of a shared task? I didn't know if there was anything that you thought around that, or you had any comments on that.
Yeah, so it is a difficult one in the sense that, as you say, we always see more cooperative robots. I call them always like coexisting robots or cooperative robots. There are actually a few taxonomies which define collaboration. So there is the things that I'm talking about are mostly the tasks where you have a continuous contact with the robot. So the wheelchair, because you're sitting on it all the time, you're manipulating it, is actually a simultaneous task. It's a perfect shared control task because you're actually touching, and then you have the force manipulation. Carrying objects together, it is like joints, for example. In teleoperation, I think teleoperation is also a very tightly physical task, because when you think about it, even if you're only manipulating a robotic arm, the other arm that is maybe assembling objects or doing some kind of complex task in the remote end is also very much physically dependent. I think, their applicability in the robotics research is less, I think, because of the challenge of it. Because we have also many problems to solve on coexistence, manipulation, let's say. Not many people work on it, but I think that is one of the most futuristic things that you can do. Like there are robots who you can dance with and so on, which could happen maybe later than others.
Absolutely, yeah. I was thinking around sort of assembly or manufacturing, and that was sort of in my mind as well. So Mark's got his hand up.
I think the heavy, bulky objects, for example, there is a lot on construction business. When you think of it, you can't have industrial robots in construction when there are people. You can't have collaborative robots because their payloads are so small, and they are small because they are deliberately small to not harm the people. But looking into these technologies, how you can understand how much you can actually support a person is very important, because those kind of tasks are completely manual labor. I think there's a lot in the agricultural domain as well, where you carry stuff, where you take a lot of loads and then you injure yourself, and you can't actually have a robot because the mechanisms is very difficult.
Yeah. Thank you for that, Mark.
Yeah, so actually you started touching on this, because I mean I've seen cobots being the big promise for a long while now. And I'm still, we've had also a lot of discussion with other people recently in the food industry who have invested into cobots and don't quite know what to do with them now. Let's put it like this, right? Mm. So because I mean, the general premise of having robots that you can work with and you can collaborate with, that you share the task with, they do some part of the task, you do some other part of the task. Most of the work I've seen so far were either academic toy examples where you kind of constructed a task, put something in a hole, like the typical put this together in a hole, or play with I don't know, an assembly task where the robot holds it and the human does something dexterous with it. I feel now, after having talked to a number of people, that not yet convinced that this whole premise around cobots is actually flying and is the way we go. We see more and more work. We want to get rid of the cages of robots, right? So that we can be co-located without being harmed. So this is, I think, what you said, cooperative maybe, but not collaborative. And I wonder if you had any thoughts on what the premise could be for truly collaborating robots. I mean, also the carrying thing is good, but in the end, you know, I've not seen much uptake of this. Is it because the technology just is inferior at the moment, and if once we make it work properly, there will be big use cases, or is there something potentially wrong in our? Is it a technology push rather than an application pull that we're doing here?
No, I think there are use cases. Honestly, I think many of the work that people do is not very humanitarian, that you definitely injure yourself, and it's very bad. If you can have a robot that would actually improve a lot of things. So I think there is a certain need, but getting those robots into that is so difficult that it's not actually coming, it's not flying. And I think one part of it is that not many people actually work on it, on this kind of applications, I think. And because of that, we haven't really seen too much advancement in that area, because there's still, even if you share a workspace with a human, coming up with the safety standards is almost coming up. For example, there are force limits, etc. But even we talk about using robots with elderly, unhealthy people, etc. And for example, there are no standards for a robot that can stand next to that person, not really touching. But then think about, for example, exoskeletons or orthotic devices and so on. They are also quite physical, quite tightly coupled. And I think there is better work in that area. So if those things can work from a control point of view, and if they can be more intelligent, I don't think there is too much boundary in terms of the applications that we can think of in enabling a robot that can actually proactively carry something with you. But it is a neat thing, I guess. Like, are people or are companies at that stage where they have the proper support personnel, they have the proper learning efforts given to having that robot to work within their systems? I think there are boundaries in many places, but somehow I think there's also a need to show that there could be some advancements, there could be some more proactivity from the robots, and that it can actually complete some tasks without being very, very harmful or without being very, very unuseful.
Yeah, thanks. I'll give others a chance. I've got more, but
Let's see.
I don't know. Thanks.
So again, I'll throw this open to the floor. Please put your questions in the chat. They'll be prioritized, and we'll put them forward. Anyone on the panel, over to you. If you have any questions, that would be great.
Yeah, I was wondering, just a curious question, I guess. So when you were driving the wheelchair around with the kind of as a kind of co-controlled object, what does that feel like subjectively, and what kind of things do you have to pay attention to in order to make that like a pleasant experience?
From the remote person's chair, or from within the wheelchair?
From the person in the wheelchair's point of view.
So when driving the wheelchair, with autonomous control or only driving it? There are so many aspects.
I kind of meant particularly with the autonomous, with the kind of shared control.
So to me, it was, I think, very difficult at the beginning. I kind of learned it quite quickly. There are certain aspects of driving a wheelchair, because it's quite a bulky device that you can't really get hold of. And there are, as you may imagine, certain difficult things such as opening doors and so on. But also, you know, there are places that you really can't see when you're driving a wheelchair, which is not really tackled in many of the intelligent wheelchair research, because we all think about the wheelchair as a proper robotic device. We put our LiDARs, and we don't actually look at look at the floor, look at the gaps, look at the patterns in a corridor or like an outside environment, which people actually have problems with. So for me, it was, I did learn it quite quickly. Working with the autonomous controller, it was, I think, interesting. And one of the one of the reasons I put a haptic joystick on the wheelchair was because it was actually guiding me. I was always under the impression that the robot was malfunctioning. So it was kind of guiding me to somewhere and I couldn't understand, and I implemented it, so I knew. But I thought that there should be some kind of mechanism that tells the person that this is actually intentionally guiding you. So if I hold your hand and push it into a direction, you could at least feel that the robot is intentionally trying to do something. And that was, I think, one of the interesting observations that I had. Yeah.
Cool, thanks.
Yeah, interesting. Yeah, interesting. So we've got a question in the Q&A chat panel from Gray Churchill. Is there a duty of care imposed on the robot when collaborating in a task that's difficult for the human? For example, lifting an object that's too heavy to lift safely, the robot could object to protect the human.
Yeah, I think that is an interesting one. I think there should be. Maybe not only for the lifting thing, but for many applications, I believe the robots have a very non-collaborative role. For example, in therapy, in rehabilitation, for example, if you put a robot, if you put a person that helps you, basically the role of that secondary agent is always to conflict you almost, because you're not doing that task correctly. And I think we don't have much of it in the domain, that we always think that robots are our helpers, our slaves, something like that. And they kind of rely on the fact that we do know the best. But I think it's a nice twist to it that the robot actually says, no, you're not actually safe, you're not actually doing it correctly, so you shouldn't do it, and I'm not allowing it. Unless you say, you're very strong to say otherwise. I think that's a nice one.
Yeah, interesting perspective. Rupika, I saw you had your...
Yes, I did. Hi, Ayse. This is the second time I'm talking to you after you interviewed me.
Yeah.
So thank you for finding me worthy enough of being in the CDT program.
Oh. So modest.
All right. My question is related to safety. I have an interest in collaborative robots, more in the autonomous domain. So I always classify safety as perceived safety and actual safety, right? Like, for example, with the wheelchairs, probably there is a system to avoid a collision. Like, say, there's a LiDAR system, safety system, which breaks down. But another thing which is a threat aspect, like the human feels scared when they're actually approaching, say, a wall or something. The robot would probably solve, but they don't know it. So that is what I would define a term as a perceived safety. So for this, I've been looking, for my own work, I've been looking a little bit into proxemics and also into human psychology. Have you come across this much more in, when you were trying to do collaboration between humans and robots in an autonomous domain?
So is the question about whether it's a real concern, or is it only the human is feeling anxious about the tasks?
Yeah, how important is it to address the perceived threat by a human? Or is there some much work going on in that area?
Well, I think it is important. The person who's using a device shouldn't really feel under threats or under danger. So if they are kind of feeling, or if you can sense that the person is actually afraid of the task, afraid of completing the task, you should adjust maybe your parameters so that you can give a chance to the person to adjust to the task as well. So for example, I think this is something that we do when we are also carrying objects. I give that example all the time, but there's a lot of sensory motor communication going on there. And then, for example, if you're carrying something with a person, or even like, this is a very nice example. So if you have another person and try to carry a pen like this, and very, very quickly, you kind of very quickly adjust your muscle actuations so that you don't actually drop it. And if I do it very, very quickly, you would drop it because the other person is not actually comfortable, and you actually failed to adapt to that person, and that's why that person is not comfortable. And that kind of closed loop understanding, I feel, should be integrated in collaboration if you're giving something like a guidance to the person, because too much guidance is always bad. Too quick guidance is always bad as well, unless you're trying to do something deliberate.
Yeah, thanks, Ayse.
Yeah, interesting question. And actually, Tetha in the Q&A chat panel has a similar, a question along a similar vein. And so for the bit of disconcern on the robot driving the chair, what do you think might aid in giving comfort to the passenger? A possible map view with routing or audio confirmations are either possible, say, in autonomous driving?
What kind of cues that you should give to the person? That I don't know, because I don't really work on too much multimodal interaction, especially speech, etc. It depends probably on the task, but the more modalities that you give, I know that the easier the information gets to be understood, but the more cognitive load you get. So if it is, for example, a driving scenario, you don't actually want to overload the person with a lot of peripheral information. If you put, for example, a screen-based interface on a robot, those are the things that we typically do for implementing a secondary task, which would actually distract the person. So from a personal choice of view, because my interest area is in haptics, I look at how we can actually give more haptic cues, maybe give more things that you can feel through your body. And it could be things that you learn how to use, like bracelets, etc., or certain sensations. That could be okay. I think depending on the application area, obviously, like with your phone, in the car, I always use the speech interface because I can't use anything else. When I'm at home, I always enter my password, for example. When I'm walking, maybe I use some of the fingerprint interface. I think it's very context dependent as well. I don't know the answer. It needs like a proper investigation of what user experience those kind of cues generate.
Yeah, interesting. And just quickly have a look at the chat for 2 seconds.
Sensation in lieu of visual and audio cues. Well, if you can, I think, yeah, the tactile and audio cues, they do work very well together. Visual to me is very, very easy to process, but very, very difficult, very, very information heavy. You have to look, you have to really like posturally look, and then you can't process anything. For example, for driving, visual cues are quite dangerous, actually.
Yeah, interesting. So it's just gone 4 o'clock. So as with when you go into a shop, if you get in just before the door closes, they're obliged to sort of stay open for you. So I encourage anyone to put a question in the comments, and we will make sure it gets gets answered. I'll ask the panel if they have any burning questions. If not, then I will sort of. Mark has a burning question. He's
absolutely. I need to bring it back to agriculture. And I need to ask this because you've shown us coming back from the shared control to the cluttered objects earlier on. We've got a lot of clutter, huge amounts of clutter in agriculture, from strawberries growing in bunches to yours on a wheat field, whatever, right? You name it. You've got lots of clutter, and these sort of paradigms that you've shown, maybe that we need to find our way into a clutter to find something specific in there. I think it's quite essential for a lot of the works that when we come towards selective harvesting, right? Pick an apple from an apple tree, find your way through the branches and push them aside, etc. So we started doing some work in that ourselves. But what's the sort of, what would you say? What is the sort of right approach to tackle this? Have you got any suggestions? Could we learn? I mean, the general approaches are learning from experts, so trying to learning by demonstration. Do we try to learn from teleoperation to have a similar kind of, matching between state that the operator has with that, or do we go with more reinforcement type of learning where we just kind of try to emulate this as best as we possibly can to then do a domain transfer, or something even better idea than whatever I come up with?
Well, if you can ground truth your data, that is the problem, I guess.
No.
Because our reinforcement learning approach does work with the ground truth. So that kind of relies on there is a ground truth segmentation image or a segmentation image that you can use to at least identify that you're at a good state or a bad state. I think it could be I don't know, some active perception could be probably helpful. What I'm thinking to go as a next step to this one is actually to do these pushing actions to see the scene better in a way that you have a camera and you're actually looking at maybe a better object identification. So you kind of maybe move towards optimizing that scene, that camera image that you get by pushing leaves around and taking a photo by manipulating, not only looking at different angles, because I think that is done in active perception quite a lot. You change your camera view and you try to find a nicer perspective to the object, but we can probably easily integrate them together to interactively manipulate and interactively take the photos, and then that could help with the manipulation, because then you could have a better maybe understanding of what is going on in the scene. I think there is a lot to learn about the agriculture, which you obviously know much better than me, about how actually, what is the strategy of the person that performs that task. And that could be maybe inspiring for the robot to handle as well, not necessarily saying that the robot should actually follow the human example, because maybe the robot could have a better way of doing it from a robotic point of view. But yeah, it is a difficult one. I think with the plants, it is a very interesting area. I'm really open to maybe sharing and then trying to do something together on that. It would be quite interesting for me.
Great. Thanks a lot.
Yeah. Thank you.
So fantastic. So I don't see any questions in the chat. I don't know if the panelists have any further questions, but we've just sort of gone 4:05. So if that is that, we'll probably look to come to a close. So I'd really like to thank Ayse for a fantastic discussion today. It's incredible what you can learn in an hour. So thank you very much. Thanks for your time today. And as you know, it's not my place to invite you, but we do have Rhizome, and you are welcome to attend and come and do some work there. So.
If you invite, welcome. Yeah, but thank you, Gary. It was like fabulous management of the whole seminar. And thank you everyone for inviting me, having me here. I really enjoyed meeting you and hope to meet you in person as well, hopefully soon.
Wonderful, brilliant.
Yeah.
So,
thank you, everybody. Thank you, Gary, for brilliant hosting, and Ayse for being around, even if it's not quite here.
Okay, so everyone, go enjoy the sunshine, and we will see those who we will see on Monday. So goodbye for now.
Bye-bye.
Bye-bye.